In this unit, we cover different sources of energy and how they relate to climate change and other environmental problems. We'll discuss non-renewable and renewable energy sources and the advantages and disadvantages of each. So it's tempting to label all renewable sources as good and clean and all non-renewable sources as bad and polluting. But like everything in life, it's a lot more complicated than that. This is Unit 3, Energy and Climate Change. After this unit, you should be able to list examples of renewable and non-renewable energy sources and explain the advantages and disadvantages of each. Describe the connection between slowing climate change and restoring and protecting natural spaces. Describe how solar electricity generation varies throughout the day. Define the concept of net energy. And explain the importance of electrification. So there are a lot of different characteristics of energy sources that should be considered in energy decisions, including geographic distribution, so where on the planet are they located, which plays into if we need to move them to where we want to use them. Portability, how easy or difficult is it to move them? Do they require tankers and pipelines? Versatility, so how can it be used? In what kind of applications? For example, gas is used for heating and transportation mostly. Volatility, is it going to blow your house up if there's a leak? And is that important to you? Reliability, is the output consistent, or are there times when it's not available? Pollution. Does using it negatively impact public health? Does it pollute the air, water, or soil? And obviously, climate impacts. Is it increasing the concentration of greenhouse gases in the atmosphere, which is undermining our previously stable and predictable weather patterns? So we remember from Unit 1 that 99% of Earth's energy comes from the sun, and we supplement the sun's life-sustaining energy with commercial energy. Commercial energy, which we humans sell in the marketplace, comes from a variety of non-renewable and renewable sources. So let's start with the non-renewables. Non-renewable energy exists in fixed amounts, meaning there's only so much of it, and when we use it, it's gone, at least in human timescales. And it took millions of years for it to form. Non-renewable energy includes fossil fuels, which are coal, oil, and gas. Fossil fuels are stored carbon. They're combustible, and they're in the Earth's crust, so we can dig them up and pump to extract them. Let's look at how each of them is formed. 300 million years ago, the climate was not the same as it is now. Most of the planet was warm and mild, and there was a lot more carbon dioxide in the atmosphere. There were huge swamps that were filled with plants, many species that don't exist anymore. So as we know, decomposers like bacteria and fungi, they generally decompose plants when they die. However, when some of these swamp plants died, they were covered with water, which prevented them from decaying very much. Over time, more and more plants piled up, and eventually sediments piled on top of them. Many, many years passed, and heat and pressure converted the non-decomposed plant material into carbon-rich rock called coal. The layers of sediment on top of the coal were converted into sedimentary rock. Coal is a solid, combustible mixture of organic compounds with between 30 and 98% carbon by weight, mixed with various compounds of water and small amounts of sulfur and nitrogen compounds. Geologic activity raised the layers of coal and sedimentary rock closer to the Earth's surface, which makes it possible for us to dig it out. Coal is burned to produce electricity in power plants. Crude oil, or petroleum, is a black, gooey liquid made of a mixture of combustible hydrocarbons, which are compounds containing hydrogen and carbon atoms, and small amounts of sulfur, oxygen, and nitrogen. This is what it looks like before the refining process. Oil is the most used commercial energy source in the world, and the most widely used energy source in the US. Oil formed when huge amounts of microscopic aquatic organisms, so tiny little animals living in water, died and settled in sediments. As the bodies of these organisms piled up, when they decomposed, they sucked out the oxygen from the sediments. So this oxygen-deficient environment stopped the decomposition process. Over time, they were buried deep in the sediments. The heat and pressure of being buried turned them into a mixture of hydrocarbons, which again are molecules that contain hydrogen and carbon. So when we burn oil, we're using the energy stored in the bodies of organisms that lived millions of years ago. You'll hear people say natural gas, but gas is made up mostly of methane. Natural gas is a mixture of gases, with about 50 to 90% methane. It also contains smaller amounts of hydrocarbons, such as propane and butane, and small amounts of highly toxic hydrogen sulfide. Gas is widely used for cooking, heating, and industrial processes. Fossil gas was formed basically the same way as oil, only at higher temperatures, generally over 200 degrees Fahrenheit. Essentially, over millions of years, the remains of organisms were converted to oil or gas, and the sediments that covered them became sedimentary rock. So oil and gas are generally found together in the Earth's crust. What's the main component of fossil gas, also called natural gas? The primary component of fossil gas is methane, which is a really potent greenhouse gas. So fossil fuels are coal, oil, and gas. Just like plants capture solar energy and carbon dioxide by photosynthesizing today, that same process hundreds of millions of years ago created the fossil fuels that we use today. So when we burn them, we're burning the solar energy and chemical energy from millions of years ago. Can you name the fossil fuels? Coal, oil, and gas are the three main fossil fuels, and they come from ancient organic matter, and we burn them for energy. Like concentrated sunlight or high-speed wind, the energy released when we burn coal, oil, and gas is actually very useful. What I mean is energy varies in quality. That is, some types of energy are more concentrated than others. Energy quality is a measure of the capacity of an energy source to do useful work. High-quality energy is concentrated and has a high capacity to do useful work. So, for example, only a small amount of useful energy can be extracted from a bucket full of wood as compared to the amount of energy that can be extracted from the same bucket of gasoline. Despite their high quality in terms of the energy that we get from them, there are many disadvantages of fossil fuels. And those problems can be put into two categories. So, problems that result from obtaining them, so the production and transport, and the problems from burning them. So let's start with coal mining. So there's different kinds of coal mining: subsurface or underground, and surface mining. With surface mining, all the plants and rock are stripped away, leaving huge wounds on the land. This obviously destroys any habitat that was there, including human communities, and the removal of topsoil prevents plants from growing back as they normally would. There's also acid and toxic mineral drainage from surface mines, which leaves waterways polluted with sediment and acid mine drainage when rain seeps through the minerals that are exposed in mine waste. One of the most land-destructive types of surface mining is mountaintop removal, which is exactly what it sounds like. So removing the entire top of a mountain to get to the coal below the surface. Okay, moving on to oil. Petroleum, or crude oil, is a liquid made of hundreds of hydrocarbon compounds. During the refining process, the compounds are separated into different products like gases, gasoline, jet fuel, heating oil, asphalt, and different petrochemicals, including plastics. So different products come out at different boiling points. You may have seen these towers before. They're for refining petroleum. The petroleum is separated into different products based on their boiling point, with the highest boiling point at the bottom of the tower and the lowest boiling point at the top. For example, asphalt has a high boiling point, so it would be produced at the bottom. Diesel oil would be higher up, heating oil would be higher, jet fuel would be higher, gasoline would be higher, and other kinds of gases with lower boiling points would be higher on the towers. So the lower the boiling point, the higher it is on the tower. Petrochemicals come out of this refining process too. And petrochemicals are used as raw materials to make all kinds of products, including cleaning fluids, pesticides, plastics, tires, synthetic fibers for clothing, paints, cosmetics, digital devices, and many, many other things. Can you name a product made from petrochemicals? Plastic is one of the most common products made from petrochemicals, meaning they're obtained by the refining and processing of petroleum. As I mentioned earlier, oil and gas are often found together. The oil and gas that are close to the surface can be pumped out relatively easily. However, there's also oil and gas much deeper below the surface that we couldn't access until the 1990s when hydrofracking became a thing, or just fracking. Fracking is the vertical, then horizontal drilling and hydraulic fracturing to release large amounts of oil and gas that are tightly held in shale rock underground. This involves drilling deep into the earth, usually 1 to 1.5 miles down, and then horizontally for up to a mile. Then, high-pressure pumps force a mixture of water, sand, and a bunch of different chemicals. This chemical mixture is called slurry, and oil and gas companies are not required to identify what's in it. So they pump slurry deep into the earth to fracture shale rock and make cracks, and then this allows the oil and gas to be pumped up to the surface. So we're going through all of these different layers here. And as you can see, we have aquifers, which contain fresh water, which we can access through wells. So as you can imagine, there are huge environmental and water pollution implications here. All of these high energy extraction and refining processes expose a major disadvantage of fossil fuels. In addition to decimating huge swaths of land and ecosystems, poisoning water and air, it takes a lot of energy to get fossil fuels, to refine them, and then to transport them. So it takes a lot of energy to get this energy. And this is the concept of net energy. Net energy is the amount of energy you have after you subtract the amount of energy it took to get it. Say, for example, it takes 9 units of high-quality energy to produce 10 units of high-quality energy. The net energy from that energy source would be 1, which is low. Despite being a high-quality energy resource, natural or fossil gas has a medium net energy when it's used to generate electricity. This is because it takes a lot of energy to make it usable. Hydrogen is a good example of an energy resource with low, actually negative net energy. It takes more energy to make hydrogen available to us than the useful energy we get out of it. Net energy is an important consideration when evaluating the long-term usefulness of different energy sources. So how would you define the term net energy? Net energy is the energy available after subtracting the energy used to obtain, process, and deliver it. This is one of my favorite posts from Bill McKibben, and it perfectly sums up the idea of net energy and the wastefulness of our fossil fuel-based economy. If we switch to renewable energy, the number of ships crossing the ocean would fall almost in half because they're just carrying coal and oil and gas. And guess what energy source these tankers are using to move around the globe? Fossil fuels. It's just so incredibly wasteful and illogical. With so much energy going to extracting, refining, and transporting fossil energy, it's no wonder it needs to be so heavily subsidized for the system to continue to work. About $1.5 trillion annually goes to subsidizing fossil energy globally. And remember, a trillion is 1,000 billion, and a billion is 1,000 million. So that's $1.5 trillion going directly into fossil fuel subsidies annually. But according to the IMF, if you include the societal costs of burning fossil fuels, like the impacts on our health, that number goes up to 7 trillion. The last disadvantage of fossil energy production that I want to address is energy dependence. The distribution of fossil fuels around the world is uneven, meaning it doesn't exist in all places where we want to use it. So this doesn't only create issues with having to move it around, it also presents major geopolitical issues. When people compete for limited resources, that usually ends in conflict. Energy independence is when a nation produces what they need and don't have to rely on other nations to meet their energy demands. Now that we've talked about the disadvantages related to obtaining fossil fuels, let's move on to the disadvantages related to burning them. In addition to the many environmental problems with extracting, processing, and transporting fossil fuels, the biggest reason we need to phase them out is their direct contribution to climate change. So fossil fuels are stored carbon. Burning them to use the energy that they contain releases carbon dioxide, and carbon dioxide is a greenhouse gas, meaning it hangs out in the atmosphere and prevents heat from escaping into space. So it works like this. Solar radiation in the form of light waves passes through the atmosphere. Most of this radiation is absorbed by the Earth and warms it. Some energy is radiated back into space in the form of infrared waves. Some of this outgoing infrared radiation is trapped by the Earth's atmosphere and warms it, which is actually a good thing. The greenhouse effect is what makes life as we know it on Earth possible. Without it, it'd be much too cold for us to live here. As the CO2 concentration increases, more of the outgoing infrared radiation is trapped. So as we see here, with our atmosphere holding on to a lot more carbon dioxide, a lot of these infrared rays that would be going out into space are being bounced back. So that heat, that energy is a mechanism for global warming. So this issue is what's causing and amplifying so many problems. The concentration of carbon dioxide, CO2, and other greenhouse gases in the atmosphere is much too high, and it's increasing because of human activity, mostly because of the fossil fuels that we're burning. Ever since the mid-1800s, humans have been burning increasing amounts of fossil fuels, which is throwing the Earth's natural balances out of whack. Some evidence of this is the increased global temperature, droughts, floods, wildfires, forced migration, biodiversity loss, and a whole lot more. Back before we started burning fossil fuels, the planet was able to absorb the CO2 that was released from natural sources like decomposing plants, volcanic eruptions, naturally occurring wildfires, and animal burps. The systems that pull carbon dioxide from the atmosphere are called carbon sinks. So we have carbon sources, which we've been discussing, and carbon sinks, these natural processes. Healthy ecosystems like forests, oceans, and coasts, and even healthy soil absorbs carbon dioxide. This image from Project Drawdown shows the sources of greenhouse gas emissions on the left and the sinks on the right. So we can see that about 40% of the greenhouse gases are absorbed or sequestered by land sinks and coastal and ocean sinks. So these are healthy, either terrestrial ecosystems like forests or coastal and ocean ecosystems. These natural processes have protected us for a long time, but now there's evidence that the amount of carbon dioxide absorbed or sequestered naturally is starting to slow down. Many companies are working to imitate Earth's natural processes and manufacture carbon sinks, but they're not close to being at the scale we need yet. So this really shows why it's so important to restore and protect natural spaces, especially forests, wetlands, coasts, and oceans. In addition to phasing out fossil energy, we need to support the Earth's ability to keep protecting us from ourselves by protecting natural sinks. So how does restoring and protecting natural spaces help slow climate change? Healthy natural spaces absorb carbon dioxide, which is a major greenhouse gas, and this helps prevent that carbon dioxide from going into the atmosphere. Let's move on to the advantages and challenges of renewable energy sources. Unlike non-renewable energy, renewables are replenished or renewed by natural processes within a relatively short period of time. Most often, people lump inexhaustible energy in the renewable energy category. So inexhaustible energy are sources like wind and solar, so they can't be exhausted or used up. So renewable energy sources include energy from the sun, which is solar power, energy from movement of air or wind power, flowing water, hydropower, biomass, which is energy stored in plants, and heat from the interior of the earth, which is geothermal energy. So let's start with solar. There are direct and indirect sources of solar energy, and solar energy can be passive or active. Direct solar energy is what helps you see during the daytime. It's what you feel in your skin on a sunny day. Direct solar is solar radiation coming directly from the sun to you. It hasn't been changed at all, it's just sunlight. Indirect solar energy is when there are multiple transformations of sunlight that result in something we can use as energy. For example, we can use the energy from burning biomass or plants. But that usable energy started as solar radiation, and the plant transformed it through photosynthesis. Other examples of indirect solar energy are wind and hydropower. So how does sunlight end up as hydropower? Remember, hydropower comes from dams. Solar radiation warms the oceans. The ocean water evaporates, then condenses into rain and feeds rivers, making it possible for us to use dams and turbines to convert the flowing water into hydropower. Active solar systems are the arrays we're typically used to seeing, the photovoltaic panels that turn solar energy into electrical energy. And passive solar involves using solar energy as it is, without moving it through wires or using a heat-absorbing fluid. Passive solar can be in the form of water tanks, adobe or brick walls that absorb the sun's heat during the day, keeping it cool inside, and slowly releasing it at night, keeping the temperature nice and warm. One of my favorite examples of passive solar is skylights. Why build a structure that's dark inside and install energy-intensive lighting when you can have skylights and use sunlight during the day for free? There are so many advantages of solar energy. Once you get your system set up, the energy source comes right to you. There's no need to move it around on tankers or fight with other countries to get it. There are also very low emissions associated with solar, very low land disturbance, and the cost is moderate, especially when compared to fossil energy sources, which require continuous extraction and processing. The disadvantages of solar include the need to have access to the sun, which can be blocked by trees, clouds, buildings, and the sun doesn't shine at night, so solar systems require backup or storage to use the energy around the clock. Another disadvantage is the high installation costs. Also, solar farms can take up a lot of space. But if we consider how many parking lots and roofs there are in this country, it makes sense to have solar systems set up on buildings like hospitals, community centers, schools, and libraries to meet the energy needs in their immediate area. So this would be a microgrid. So rather than using huge swaths of land for solar farms and then moving that energy through the grid, microgrids really just provide the energy that they need for their immediate area. So it doesn't have to travel very far. How does solar electricity generation typically change throughout the day? Solar electricity generation is highest in the middle of the day when the sun is the strongest. Okay, moving on to wind. The kinetic energy of the wind can be captured and converted into electrical energy by wind turbines. As the blades of a turbine spin, they drive an electric generator, which produces electricity. And wind has high net energy. Wind is widely available and produces low-cost electricity. Energy from the wind has little or no direct emissions of carbon dioxide, which is a really big advantage. And wind farms are relatively easy to build. Some downsides of wind include the need for backup and or storage when the wind isn't blowing. Some people don't like the way wind turbines look. If not properly located, wind turbines can kill birds and bats, however, in very small numbers compared to other threats. Power lines, windows, and domestic cats kill more birds annually than wind turbines. Cats kill between 210 million and 3.7 billion birds annually, compared to 20,000 to 570,000 birds killed by wind turbines annually. That's still a lot of birds. Hydropower is technology that uses kinetic energy of falling or flowing water to produce electricity. It's the world's most widely used renewable energy resource. Hydropower has high net energy and provides low-cost electricity. It also produces very few emissions after the dam is built. However, dams have several serious disadvantages. When you block the flow of a river, you not only flood everything upstream, you block the movement of animals, which negatively impacts the ecosystems in the water and around the river, and it also prevents the flow of nutrient-rich soil, which could be used for farming. Also, a lot of plants get stuck and decay behind the dam, which releases methane, and as we know, that's a potent greenhouse gas. What's a disadvantage of hydroelectric power? One major downside of hydroelectric power is that dams can disrupt rivers, harm fish populations, and change natural water flow, affecting ecosystems. Biomass is also a renewable energy source, assuming it's not used faster than it can grow or replenish. The simplest way to think of biomass is firewood, so burning the organic matter in plants. Animal waste is also used as biofuel. Biomass can be burned as a solid fuel or converted into liquid biofuels, so think of ethanol, which is ethyl alcohol from plants and plant wastes. Biomass as an energy source has some pretty major disadvantages. Biomass used for cooking inside can lead to respiratory disease. Wood gathering contributes to deforestation, which creates a cascade of other problems. Burning biomass doesn't have a net carbon dioxide increase, but plants are much more valuable to us alive in the long term than dead in the short term. That's because they sequester carbon, provide habitat, shade, food, medicine, comfort, beauty, and so much more. It's important to consider land use issues related to biomass if we were to use it at a large scale. For example, it would take a lot of land to grow enough corn to make ethanol to replace jet fuel with sustainable aviation fuel. Geothermal energy is heat stored in the Earth's mantle. It can be in soil, rocks, and fluids. This heat can be used to warm and cool buildings, heat water, and produce electricity. Geothermal energy is available 24/7, but only in locations with high enough concentrations of underground heat. Here we see a geothermal heat pump, which can heat and cool homes almost anywhere in the world. This kind of system uses the temperature difference between the Earth's surface and underground at a depth of around 10 to 20 feet. At that depth, the temperature is typically 50 to 60 degrees Fahrenheit or 10 to 20 degrees Celsius year-round. The buried pipes contain a fluid that absorbs underground heat in the winter and moves it into the home. In the summer, it works in the opposite direction. It extracts heat from the home and stores it underground. Some advantages of geothermal include lower emissions in fossil fuels and low operating costs. However, geothermal isn't feasible in many places and has a high cost to set up. We can't talk about energy without including nuclear, so let's do it. Nuclear power plants perform a relatively simple task. They boil water to create steam, to spin a turbine, to generate electricity. What makes nuclear power so expensive and complex is it uses controlled nuclear fission reactions to provide the heat to boil the water. Nuclear fission is a reaction that produces a huge amount of energy in a chain reaction. It uses uranium, which has to be mined from the earth, and then it's enriched. So this process creates highly radioactive material that has to be safely stored for literally thousands of years. The advantage of nuclear energy using fission is that it emits much less CO2 than coal. But there are serious disadvantages, including low net energy, because the entire nuclear cycle is really energy intensive. Nuclear energy has high overall costs, and it produces incredibly long-lived harmful radioactive waste. A really important consideration is that nuclear power can promote the spread of nuclear weapons, which really shouldn't be understated. Some proponents of nuclear power see fusion as a promising answer to some of our energy problems. Nuclear fission, which is a process we're using now, involves splitting a heavy atomic nucleus into lighter nuclei, releasing energy. Whereas nuclear fission is a process where two light atomic nuclei combine to form a heavier nucleus, also releasing energy, but through a fundamentally opposite mechanism. This image and the next one summarize about everything we've covered in this unit. As you can see, about 85% of commercial energy used in the world comes from non-renewable sources. So even if climate change wasn't a problem and the environmental destruction caused by the extraction of these energy sources wasn't a problem, we still face the problem of using finite resources faster than they'll replenish. Remember, it took fossil fuels hundreds of millions of years to form, and we're burning them up in a geological instant. Once they're gone, they're not going to be replenished on a timescale that makes any sense for human societies. Even though the use of renewables is increasing, unfortunately, the use of fossil fuels is also increasing. So the U.S. continues to expand oil and gas permits on public lands, and unfortunately, this happens under both Republican and Democratic leadership. The U.S. is the world's biggest producer of oil and gas, and this keeps expanding. When we look at the pros and cons of different energy sources, we can consider how safe they are and how clean they are. Of course, there are lots of other considerations, as we've seen. When looking at death rates from accidents and air pollution and greenhouse gas emissions, it's clear that fossil fuels are both the most dangerous and emit the most greenhouse gases per unit of energy. On the other hand, the energy sources that emit the least amount of carbon dioxide, so solar, nuclear, wind, and hydro, are also the safest in terms of deaths from accidents and air pollution. In summary, both from the human health and climate perspectives, we have to stop relying on fossil fuels. So if we could rework our energy system and create one that doesn't undermine our ability to live on this planet, what would that look like? What we know for sure is that we must stop producing carbon dioxide and other harmful greenhouse gases. And that means we have to phase out or at least dramatically reduce the fossil fuels that we use. So think of things that still use fossil fuels. Industrial practices, water heaters still use gas, and stoves and space heaters use gas. So while electric vehicles are becoming more popular, still the majority of vehicles in the US are powered by gasoline. Also, what we don't see are the energy sources of local utilities. Many utilities still use mostly fossil gas to produce the electricity that we use in our homes and businesses. To phase out or phase down fossil fuels, we have to electrify everything. So you may have heard that, electrify everything, including heating, transportation, and the sources used by utilities. But we don't have to electrify everything. Think about hot water, for example. Does it make most sense to have an electric heat pump to heat your water? Or is there a way to just use passive solar to heat your water instead without electrifying it? So we have to think about all these different alternatives. So to electrify most things, the electric grid has to be able to handle a lot more electricity. And another thing we have to consider is that coal, oil, and gas are high quality energy and they're reliable. That means with the infrastructure to support them, they provide consistent energy. And we want that part. That's the part we want to keep. The consistent energy without disruption. But we need to replace the source. This means we're going to have to knit together different kinds of renewable energy sources to make sure we have reliable energy at all times. So for example, the sun only shines during the day, and the wind doesn't blow all the time. So we have to figure out how to use these sources and other sources together and to store the energy when it's abundant so we have access to it when it's not. And that's where batteries come in. Another thing to remember about fossil energy is it's very highly subsidized, which makes it artificially cheap. Moving subsidies and tax breaks from non-renewables to renewables would go a long way towards speeding up the transition. Of course, that requires political will, which won't happen without the population demanding it. So why is electrification important in modern society? Electrifying everything would enable cleaner, more efficient energy use and support renewable energy sources. Transitioning away from fossil fuels brings about a new set of questions such as energy storage, battery technology, and getting an energy supply from multiple intermittent sources rather than a few steady power plants. Transitioning away from fossil energy presents enormous challenges, political and otherwise, and enormous opportunities. If we get it right, if we listen to this call to action, we can build a future energy system that's more equitable and doesn't undermine our ability to live on this planet. In this unit, we address the different sources of renewable and non-renewable energy, including their advantages and disadvantages. We define carbon sinks and how restoring and protecting natural spaces is crucial for the planet's ability to continue absorbing a big proportion of the carbon dioxide we spew into the atmosphere. We mentioned a disadvantage of solar electricity generation in that the sun isn't always out, so we need to pair solar systems with storage. We talked about net energy as the total high-quality energy we have after we subtract the high-quality energy needed to extract, process, and transport it. So basically, the usable energy minus the energy it took to get it to us. We also talked about the importance of phasing out fossil fuels and electrifying most things.